next problem is called the find median from the data stream, and the median is the middle value in an ordered integer list. If the size of the list is even, there is no middle value, and the median is the mean of the two middle values. So if you have, for example, 1, 2, 3, and 4, the number of elements is even. In this case, is 4 elements. So the median is basically the average of these two. In this case, we will have 2.5 for the average, and that would be the median. If we have the odd number of elements, for example, 1, 2, 3, then the median is basically just the middle element, in this case, 2. Now, we have to implement the median finder class, which has the constructor, which initializes the median finder object, and basically two methods. The first method is a write operation, insertion operation, which just passes the number that we want to add basically from the data stream to our data structure. It's important to note here that we have a data stream, so we will be basically periodically getting periodically the new elements. So we don't have a fixed size, we don't have a fixed input. It's basically a stream. So we have 1, and then maybe after 2 seconds we have 2, after 3 seconds we have 3, and so on. Then the read operation, in this case, is the find median, which returns the median of all elements so far. Answers with the 10 to the minus fifth of the actual answer will be accepted. This is just because of the rounding error that we have. Now, the thing to note here is that the solution where we sort the elements that we currently have, that we have taken from the stream, is not really the optimal one, and so it's pretty slow actually, because we could be calling the median every single time after we insert a new element from the stream. So that means that for each read operation, we would have n times log n, where n is the current number of elements that we have taken from the stream, which is not optimal. We would be wasting a lot of time here. So we have to optimize. We have to optimize on the read path. So basically on the write path, we have to optimize so that on the read we are reading the data much quickly. This is a common exchange between the time spent on the writing path and on the reading path. In this case, we know that reading should be fast, so we can spend more time on the writing. Now, to solve this problem, before we get to the idea, first let's just check the constraints. Now, for the constraints, we have the following. The numbers can be from minus 10 to the fifth to 10 to the fifth. There will be at least one element in the data structure before calling the find median, and at most 5 times 10 to the 4 calls will be made to add num and find median. So we can be sure that we will not call the read operation find median if basically we haven't taken any element so far. A common data structure used for finding median in data stream is a combination of min and max priority queue. And how can we utilize two? So we will be utilizing two min and max priorities queue to basically to get the read, to get the median in a constant time. So first thing is that there are actually two things that we have to worry about. The min priority queue will hold the larger group of numbers. Like when we say larger, those are the elements that are the largest in the stream that we have added. And the top of that group, the element that will be at top of the priority queue is actually the smallest number of the group which contains the largest element. So it's kind of in the reverse order. So basically in the minimum priority queue, we are placing our larger numbers, while in the maximum, we are placing the elements that are smaller, that represent smaller elements. So basically, if we have 1, 2, 3, and 4, 3 and 4 will be placed in the min priority queue, and 1 and 2 will be placed in the max priority queue. And why are we doing this? Because in the max priority queue, the element at the top will be the element that's largest from the elements in the first group. This is basically the element 2. While for the minimum priority queue, the element that will be at top is the element that's smallest from the numbers that basically represent the group which contains the larger number groups. So in this case, we will have 3. So basically, we can just get the top of minimum and top of maximum and basically compute their average to get the median. That's why we are having this reverse relation between the min and max priority queues. Now, this is good when we have even number of elements, but if we have odd number of elements, then basically we can just, for example, 1, 2, 3. If you place number 2 in the max priority queue, it will be at the top. We will have 1, 2, and then we will have 3 here. So if we have an odd number of elements and a total number of elements, we can basically just get the element that's at top of the max priority queue, and that's basically that's the only thing that we have to do. Now we have to also, like, that's the thing that we have to take care of, is that the min and max priority queue should be roughly of the equal size. The max priority queue can have one more element, but if the max priority queue is containing 3 elements, while we only have one element in the minimum priority queue, we have to place one of the elements from the max to the min priority queue to basically rebalance the priority queue. So that's the first thing that we have to take care of. The second thing is that if we place an element in the minimum priority queue, so basically we have an element. Let's say we have 3, 4, and in the max priority queue we have 1 and 2, and we have placed number 5 in the max priority queue. So this is our max and this is our min. Now 5 is actually one of the larger numbers, so it has to go in the minimum priority queue. And we can easily check that because the minimum element at the top of the minimum priority queue will be 3, while the maximum element of the maximum element at the maximum priority queue will be 5, and basically 3 is smaller than 5, and we know that the smallest number that we have in the minimum priority queue will be larger than the maximum number that we have in the maximum priority queue. Basically, we have to have this to have this property here. As we can see here, the maximum element in the maximum priority queue is 2, and the minimum element in the minimum priority queue is 3, but 3 is still larger than 2. So we have to keep this property. So basically, we will have to discard this element we will have to switch basically the number 3 and the number 5. So 4 and 5 will be the state of the minimum priority queue once we switch the places of 3 and 5, and in the max priority queue we will have 1, 2, and 3. Now we know that the maximum element that we know that all the elements now in the minimum priority queue will be larger than all the elements in the maximum priority queue. How do we know that? Basically, we know that because once we get this 5 from the max priority queue, we know that it's larger than all the elements inside the max priority queue. So that property holds, and we know that the minimum element that we have given from the minimum priority queue to the maximum priority queue is the number 3. So once we transfer it to the max priority queue, we will have 1, 2, 3. And basically, because the property was holding before we added the number 5, we know that when we do the switch, we will basically revert to the property holding back again, because we have switched the minimum element from the minimum priority queue to the max priority queue. So we know that the max priority queue will contain the half of numbers that are smaller, while the element that we have added to the max priority queue that has been larger than the element at the top of the minimum priority queue will be then extracted from max priority queue and added back to the minimum priority queue. So the property will hold. Now let's solve the problem using Java programming language. First, we will declare our 2 priorities queues, minimum and max priority queue, and in the constructor we will just initialize them. As you can see, the default is actually the minimum priority queue, and if we want the maximum priority queue, we can just declare the collection reverse order. Next, for the add num, basically our default place for inserting an element will be the maximum priority queue, and then we will do the rebalancing between the between the queues. The first rebalancing is checking if the size of the maximum priority queue is more than 1. And in that case, basically, we have 2 extra elements in the maximum priority queue, and we have to take the top element at the maximum priority queue and add it to the minimum priority queue, so we can have the difference at most 1. To keep the first property. Now, the second property is basically if the minimum element at the top of the minimum priority queue is smaller than the element at the top of the maximum priority queue, and we know that the second property that must hold is basically to have all the elements that are larger than all the elements in the maximum priority queue. We have to have them in the minimum priority queue. So the smaller group, the elements that are smaller will be in the maximum priority queue, while all the elements that are larger than that group will be in the minimum priority queue. So we will just switch between the minimum and the maximum top of the queues. So we will extract the minimum, the element from the element at the top, basically the minimum element from the minimum priority queue. We will extract it and add it to the maximum element at the element to the maximum priority queue, while the element that has been on the top of the max priority queue will be added to the top of the minimum priority queue. Next, for the find median, we will basically check just if we have an odd number of elements, and it's enough to check if the two groups represented by the two priority queues are not the same. So we have more elements in the maximum priority queue. In that case, we will just convert the top element at the max priority queue to double, because that's what the return type of the find median function is. If you have the same elements, basically we will just take the top of the minimum priority queue and the top of the maximum priority queue and get their average. Now, for the time and space complexity, W is basically indicating the number of writes that we have, and because we are performing operation of the priority queue, we will have log to the relation of the numbers of elements that we have that we have added from the stream. So we will have W times log n plus the number of read operations, and read operation will be just constant, because we are just taking the minimum and maximum elements from the either one of the elements or one of the queues or both of the queues. Now, for the space complexity, basically we are holding in total n elements taken from the stream.